Good morning, students.
Good morning, ma'am.
Good morning. Ashwija, you're fine?
I'm still recovering.
Okay. All right, we'll start. 51 are present. Okay. All right, I hope I'm clearly audible and the screen is visible there. So we will start with the next module, that is module 2. So I suggest everyone to study module 1 properly. All the materials are shared. Today I will be sharing 2 textbooks, e-textbooks, which will help you to understand the concepts still better. Okay, so you have to do proper studying, learning things. Only when you're comfortable and clear with module 1, you will be able to understand the following modules. Okay, so, and as I mentioned, there will be a continuous assessment happening in between, with maybe some might be scheduled ones and some might be unscheduled ones. So you should be ready at every time to uh, take your continuous assessment. Okay. All right. So we will start with module 2 now, wherein we will start discussing different devices. So first we'll start with junction field effect transistor. So by the end of this class, you'll be able to describe the construction and operating characteristics of junction field effect transistor. Okay, transistor word is missing there. And you will be able to sketch the drain characteristics. Okay, so to start with, I hope you have learned about transistor, the basics of transistor in your PU. So you might be familiar with bipolar junction transistor. So you know that it has 3 terminals. It is a 3-terminal device where it has a base, collector, and emitter are the 3 terminals. And there are 2 types of transistors, NPN and PNP. So, and if you recall, the output current was collector current there in BJTs, that is transistor, which was controlled by the base current, right? So the amount of the base current applied would be resulting the collector current, okay? Or in other words, you can say the collector current, the output of the transistor was controlled by the base current. So it was called a current control device there, BJT, okay? So coming to JFET or FETs, all right, field effect transistors. So it generally has 3 terminals similar to BJT. Okay, it has 3 terminal. It is a 3-terminal device. The 3 terminals are drain, source, and gate. All right. So here the output of JFET is drain current. All right. The output of the JFET is drain current, and it is controlled by the voltage applied across gate terminal. That is the voltage across gate and source terminals. Okay, so the voltage across gate and source terminal will be controlling the drain current, which is the output from the JFET. So because of this feature, it is a voltage control device. So amount of voltage that is applied between gate and source will be controlling the output drain current. All right. So with this basic information, and um, uh, JFET is a unipolar device, which means that it operates only with one type of charge carrier. So either the current flow can be through because of holes or electrons, not both, unlike BJT. In BJT, you have both the current flowing through because of both electrons and holes. Excuse me. So here in JFET or FET, it is a unipolar device. So the current would be only through one type of charge carriers. Okay. And one more important point to note here is the JFET is a very high, has very high impedance. Okay. So wherever the application where you need high impedance, in such cases, JFET will be used. But it is not a very good device for amplification like that of BJT. BJT is mainly used for amplification. JFET are very not widely used for amplification applications. It is only used in the situation where you need high input impedance. Okay, so we will understand all these characteristics as we go on with the working of the device. All right. FETs, the field effect transistors, are broadly classified into two categories, JFETs and MOSFETs. JFET is junction field effect transistor, and MOSFET stands for metal oxide semiconductor, FETs. Okay. In JFET, again, both the devices you have in your syllabus, you will be studying both the construction and operation of JFETs and MOSFETs. All right, in module 2. So JFET, there are two types again, N channel and P channel. Okay, MOSFET also based on the type, that is enhancement type and depletion type. Both the types has again two types in them in terms of operation, the N channel, P channel in both the enhancement type and depletion type. So this is the broad classification of FETs, which you should be familiar and you will be studying in the following classes. If you want to note down, you have to quickly note down wherever required. All right. So the basic structure of the JFET is shown here. The figure on the left hand side indicates the typical construction there, the basic construction. It is shown there where you have a channel. Okay, say it can be N channel or P channel. All right, first let us discuss N channel there. So in N channel, there are leads connected, that is with the ohmic contacts, there are leads connected there. On the top you have the drain, terminal. Okay, and below the channel you have source terminal, and there is p-type material diffused in the N channel. Okay, and both these p-type regions are connected to form one terminal called gate. All right, similarly the P channel, you have one P channel there. All right, so on the top with the ohmic contact there is a terminal where you have a lead called drain, and on the bottom you have a terminal with the ohmic contact called source, and both there is N-type material which is diffused inside the P-type. All right, and there is a lead or the contact connecting both the N-type here to form one more terminal called gate. All right, please note down. So most of our discussion would be on N channel. All right, the operation, the working, we will be concentrating on N channel, which would be applicable to P channel as well. Only the polarity of the potential applied would be varying there. Okay, And on the right hand side, as you can observe, it is the schematic symbols of N channel JFET and P channel JFET. And observe that in N channel, the arrow direction will be towards, that is inside for N channel, and the arrow at the gate terminal, it will be out, facing out. Okay, so that the difference should be clearly noted. And as we go on with the discussion, you will understand what does it signifies there. What is the indication of direction of the gate terminal? Okay, please note down. I want you to note down the basic structure and their symbol. And let me know when you are done. Have you copied? Are you with me?
Yes, ma'am.
Okay. Okay. Yeah. If you are done with, we'll proceed. Oh my God, I don't know why. Okay. So the basic construction of N channel, you can observe there on the slide now. The major part of the structure.
Ma'am, the slide is not visible.
Okay. Yeah. Now it is visible?
Yes, ma'am.
Yeah. So the major part of the structure is their N-type material, which forms the channel. All right. And you observe that there is a P-type material embedded inside, right? And top of the N-type channel is connected through the ohmic contact, where we came to know that it is a drain, and the lower end you have the source, and two P-type materials are connected together to the gate terminal, right? So in the absence of the applied potential, now if you observe the working there, in the absence of, say, you have not connected these terminals to any output biasing voltages. So observe the PN junction there. Because of the PN junction, there will be always the depletion region, isn't it? There is a result of depletion region at the junction. I hope you are able to understand and recall why it is so, right? So even when there is no voltage applied, where am I? Yeah, when no voltage applied, there is a depletion region formed. So the main working of this device, the current flowing through the channel and across the terminals, it is mainly depending on this depletion region, controlling this depletion region. Okay, so how it is done and all we will discuss now. All right. So in order to operate or use and make the device usable or make it conduct, we will obviously have to go for biasing, right? So this is the typical biasing configuration of JFET. The drain and source will be connected to the biasing voltage VDD, where we say we are applying voltage across drain and source. So it is also termed it as VDS. Okay, via there is a resistance called drain resistance, which will be connected in series. And as I mentioned, the gate and the source, you will be connecting a biasing voltage VGG, all right? And it will be the voltage across gate and source. So we VGG is also referred to as VGS. All right. And you have to understand here the basic, as I mentioned, the control of the current, the output current, it is mainly due to the applied voltage across the gate terminal, that is between gate and source terminal. So by controlling the voltage applied across gate and source terminal, we will be able to control the current flowing through the device. All right. So here, how do we control that? The gate and source junction will be always reverse biased. All right. So we will understand all the working of that, how it works and all. So first, let us consider the state where the gate terminal is grounded. Okay, that is, there is no potential applied across gate and source. Please note down this biasing configuration quickly. So in order to make the device work or to allow the current to flow through, we have to bias it. So VDD will be applied across drain and source terminal, and VGG will be applied across gate and source terminal. Okay. So observe here and tell me, what can you interpret here in the figure? What is that you can observe? My question is with regards to the depletion region. What can you observe there? Hello, are you there? Can you find some difference in the structure there? Are you able to note? Somebody's replying. Decreases. What?
There is a potential drain.
No, I'm not talking about the conduction or something. I'm talking about the structure there. What? Barrier potential. Okay, what is? Fine.
Width is decreasing.
Width is increasing, correct? Yeah. All right. And in the width, are you able to find some difference there? Are you able to interpret some difference in the width there? The region is more at the end of drain. Correct? Very good, Adarsh. Okay. Adarsh has replied after so many days. Okay. Okay, fine. Yeah, very good. Thank you. So observe the figure there. As I mentioned, during biasing, when we apply voltage across drain and source, when that is VDD, when you and inside, you know, it is a N channel, right? And the majority charge carriers in N will be, yes, majority charge carriers in N type material is, unmute and speak. Yeah, electrons, right? yeah, electron. So now, let's start with the condition like when G or the gate is grounded or there is zero potential applied across gate and source. Okay, let us consider that condition. So G gate terminal, it is across the P regions, right? Both the P regions are tied together to form the gate terminal. Now, when VDD is increased, okay, when the voltage across drain and source is increased, VDS is increased, what happens? Positive terminal is connected to this drain terminal, right? As you increase VDS, what happens? The majority charge carriers in the N channel, that is electrons, will get attracted towards drain and they start flowing, right? So there is a flow of current happening, right? So we know that the conventional current, it is always opposite to that of the direction of the flow of electrons, isn't it? So as you increase VDS, electrons get attracted towards the drain terminal, okay, and there is a flow of current happening. Mind you, keeping VGS is equal to 0. All right, VGS, we have not applied any potential there across gate and source. Only we are varying VDS, voltage across gate and source, drain and source, right? So as we vary voltage across drain and source, as the potential increases here, more number of electrons from the channel, it is getting attracted and there is a flow of current. So that means the flow of current is nothing but opposite to that of electrons, isn't it? So current ID, the drain current ID, will be flowing in this direction. That is from drain to source. Okay. Observe here. The width, the variation in the width, I ask you to note that there is some difference in the pattern or the variation. So you have to pay attention there. This variation, it can be explained by assuming uniform resistance in the channel, there. Okay. So we can break this resistance in the channel into different the resistance throughout the channel. Okay. Now the current ID will establish these different voltage levels inside the channel. The current ID, the drain current, will establish the different levels of voltages inside the channel. Now, since the potential is applied across drain and the P terminal, which is gate, which is grounded, okay, all right, and you're varying VDS. Now, observe what happens. There is a increase or variation in the reverse voltage, isn't it? Are you with me? The N channel, the drain terminal, it is connected to positive of the battery, right, VDS, and the gate terminal, which is P-type material, it is grounded. So are we varying reverse voltage there? Are we varying reverse voltage? Hello, I want you to unmute and speak. Please don't chat.
Yes.
Yeah. Okay. So,
Yes, ma'am.
okay. Because of this increase in the reverse voltage, recall from the discussion what we had in the diode operation, the greater the applied reverse voltage, the wider will be the depletion region, isn't it? So because of the current flowing, the drain current, this will establish different levels of the resistance here. As you can observe, the upper region, which is say the gate terminal will be generally slightly nearer to the drain terminal. Okay, so because of this, the resistance at this level, the upper region will be say 1.5, all right, compared to the resistance at the lower area or the lower region of the channel. So because of variation in the VDS, that is we are varying the reverse voltage. As we increase the reverse voltage applied, the width of the depletion region also is varying. So because of this, you can see there is a wider region of depletion region at this area compared to the lower region. Okay, the width of the depletion region is comparatively narrow compared to the upper region here. Okay, so as it goes on, as we vary the VDS, okay, the depletion region goes on widening, isn't it? Remember here, recall the operation, diode operation, what we had there. The greater the applied reverse voltage, the wider will be the depletion region. So because of this, the depletion region here goes on widening, and this widening will be more in the upper region of the channel here, okay, compared to the lower region. All right. So what happens as it goes on widening, there comes a point where both the depletion region at the upper area touch each other. Okay. Now observe the resistance in the channel. So as this depletion region is varying or widening, what is happening at the resistance here? Can anyone tell me the resistance inside the channel? How is it getting affected? Is it increasing or decreasing? So resistance to what? The flow of current. There is it increases, isn't it? Yes, I'm getting the answer. It increases. Very good. Okay. So you're all following. Okay. Yeah. So I'm getting the answer. Now, that's what I wanted to tell you here. So there is a flow of current happening, the drain current, which is nothing but as we vary VDS, there is the current flowing through, it is getting affected because of the resistance here. All right. Varying resistance. So initially when it was quite narrow, okay, as the width was narrow, the channel had sufficient width there. Observe the terminologies what I'm using. The width of the channel was sufficient to allow the current to flow through. Okay. As the width of the depletion region is increasing, as you vary VDS, depletion region also will increase. Okay. As the depletion region widens, the width in the channel becomes less and less, right? Which in other words, you can say the resistance is increasing. Resistance is increasing means it is now stopping or it is a resistance to the flow of charges, isn't it? So there is a point where we said it is when the VDS value reaches VP. VP is nothing but a condition where there is a pinch off happening. Pinch off is nothing but a condition when both the depletion region at both the ends here goes on widening and they touch each other. You can imagine like pinching, taking your two fingers, right? Your thumb and your index finger. Okay. If you pinch like that, what you're actually pinching off this channel, blocking the channel for the flow of current. Are you with me? Are you able to visualize things? Okay. So the applied voltage, VDS, when it is equal to pinch off voltage, which we call it as VP, okay, that is when, what should be the condition of the current here now? Can anyone tell me? What should be the value of the current?
Almost zero.
Almost zero. Very good. Almost zero. Yeah, it should be almost zero, but it doesn't happen so, right? In practical scenario, there will be some little amount. It's not little amount. We say there is some constant current still flowing, even at the condition of pinch off. Okay, that is in practical scenario. All right. So that gives us a drain characteristics. Okay, this is your drain characteristics. To get this drain characteristics, this is your circuit diagram. All right, we have taken the N channel JFET there, and the voltage applied across gate and source, it is zero. Considering the condition that the voltage across gate and source is zero. All right, and VDD is applied to the gate, drain and source. I'm sorry, drain and source. Okay, and mind you, all these ground terminal, different ground terminals indicate you have to consider it to be a common ground point. All right. So when you are applying VDD, that is voltage applied across drain and source, VDS, via the drain resistance here, as you go on varying. All right. So initially, in the x-axis, you see it is VDS, and in the y-axis, you are plotting ID, the drain current. All right. So as you go on increasing VDS, observe there, as you go on increasing the VDS, there is current also is increasing. Okay. But this is a ohmic region because there is, say, resistance is also varying, isn't it? Let me go back to the structure here. All right. VGS is maintained at 0. VDS is varied. All right. VDS is varied. So as the depletion region is widening, the resistance is also varying, right? But there is still a flow of current. So current is increasing as you vary VDS, isn't it? Because the drain is made more and more positive, so more electrons are attracted toward the drain terminal, eventually resulting in drain current. So as VDS is increased, drain current also increases slowly. Okay. When the applied voltage VDS is equal to VP, that is pinch off condition. All right. There, as I mentioned, in practical scenario, there will be some constant current where the drain current will achieve a constant value. This is the condition where the resistance will be almost infinite. Remember, in the, where is it? In the pinch off condition, when there is a blocking of the channel here, that means the resistance here is maximum, right? So the straight line here indicates that the resistance is infinite, but here in this region, the resistance will be almost constant. Okay, as you are varying VDS, where VDS is below VP here, observe that. VDS, if it is below VP and if it is increasing, current is also increasing, the drain current is increasing. Okay, at this region, the resistance will be almost constant, but at this region, as VDS reaches VP, resistance increases. Look at the curve there. This curve in the plot indicates that the resistance is increasing. Okay. And when VDS reaches pinch off condition, pinch off voltage is nothing but the condition when there is both the depletion regions touch each other. Okay. At that point, as I mentioned, there will be a constant current, constant drain current, and we call that as IDSS. Okay. IDSS is nothing but the drain current keeping VGS is equal to 0, right? And it is the maximum drain current defined by the condition VGS is equal to 0 and VDS is greater than VP. All right. So if you go on increasing VDS there, all right, there can be a breakdown happening. So including all these points gives you the drain characteristics of N-channel JFET device. Go through, try to understand, and tell me if you want me to repeat any of the point, I will repeat. Do you want me to repeat any point there? So I want you to note down the circuit, draw the drain characteristics. I'll explain the graph. Yes, okay. Explain the graph. Okay, before doing that, let me show you this slide. So observe the different conditions there. The graph can be understood with this interpretation here. So this is the first condition where VDS, assume that VDS is 0. That is, the voltage applied across drain and source is 0. So obviously there will be no current, isn't it? ID, the drain current is 0, correct? So that would be the starting point of your graph. Are you with me? So this is your voltmeter VDS, all right, which is connected to the drain terminal here, all right. And to measure the current, you will always connect ammeter in series. So you're measuring the drain current here at the drain terminal. So ammeter is connected in series along with the series resistor there, all right. And VDD is connected here, which will be across drain and source, right? So when VDD is 0, drain current is also 0. So voltmeter and ammeter both are showing 0 reading, all right. So come, observe the condition B here. As VDD or VDS is increased, okay. So in the ohmic region means what? According to the Ohm's law, as V is increased, all right, current is also increasing, right? Based on again the condition of R there. As I mentioned initially, R will be almost constant, right? Say the depletion region is slowly increasing, okay, and there is a sufficient width in the channel for the current to flow through, okay. So that condition we can take it as resistance is constant there almost, all right. So in that condition, in that ohmic region, as you increase VDS, current, drain current also increase, okay. Drain current proportionally increase with VDS, all right. When VDS is equal to VP, so now observe that as you have increased VDD, VDS you are increasing and the depletion region is widening. As the depletion region across the PN junction widens, okay, there achieves a pinch off condition, which we call it as pinch off region. And the voltage at that pinch off condition is nothing but VP. So when VDD, that is VDS, is equal to VP, the current, the drain current will be almost constant, okay, in a practical scenario, which we call it as IDSS. So when VDS is equal to VP, current will be IDSS, which is a constant drain current, all right. Now the next scenario is as you increase VDS further, okay, more than that can be withstand by the device. ID, it goes on increasing and it at one time when the drain current exponentially increases would be the condition where there is a breakdown happening. Breakdown of the device is taking place, okay. So there are 4 conditions there in the graph. Let me go back to graph there, okay. So this initial condition is when VDS is less than VP. So when VDS is less than VP, VDS, as you're varying VDS, increasing VDS, current is also increasing in this condition, okay. Now all this, you have to visualize all these operation. You have to visualize this diagram. You're varying VDS, current is increasing, right? There is a width, sufficient width in the channel for the charge carriers to flow, and there is the drain current. So you have to visualize all these points together, okay. And as you're varying VDS means it is nothing but you're increasing the reverse voltage. So that is getting affected at the depletion region at the PN junction here. These two are P regions, right? And you have maintained it to be at 0. The P terminal, it is maintained at 0 potential, and you're increasing the potential at the N terminal, which is nothing but reverse bias condition. So all these points you have to visualize together and understand the working, right? So initially, as VDS is increased, current is increasing. And as VDS is increasing, as approaching the pinch off condition, resistance is increasing, and at one point, that is after the pinch off condition, resistance is infinite. That is where there is a touching of the depletion region, pinch off region, right? So we call that voltage. The voltage at pinch off condition is VP, P pinch of voltage. Okay, so at that time there will be constant drain current indicated here. Okay, please observe, in y-axis you have VDS, in x-axis you have drain current, ID. So as you're varying VDS, drain current is increasing. Okay, after VP, drain current will be constant. Okay, this is where you have constant current output from the JFET, which we call it as active region. That there is constant current there, right? So after further, the value that will be specified by the data sheets and all by the manufacturer. Okay, if you exceed the particular threshold there, VDS, there will be breakdown condition. That means where current will further increase exponentially. That is breakdown. We should never go to that condition at all. That is breakdown region. Is that clear? Please note down the circuit diagram there. This is a condition when VGS is maintained at zero potential. I'm repeating that because if we vary, in the beginning we started with the discussion that JFET is always operated with gate source PN junction reverse biased. So if we vary the reverse bias applied across gate and source, so what happens will be the further discussion which will be discussed in the next class. Okay, so in the when VGS is equal to zero, this is your typical drain characteristics. And in this topic, you can expect question on the same, that is, explain the N-channel JFET, say with the drain characteristics. So drain characteristics you still have further with increasing VGS, which we'll be discussing later in the next class. Is that clear? Do you want me to repeat any of the points here? Can anyone explain the analogy here? I have taken this from the textbook. How do you interpret this analogy? Can anyone tell me? Can anyone try? The famous textbook, Boylston, uses this analogy. What is the indication of that? How do you justify that? How do you understand that? Hello, are you there? Are you all there? Can you try? Yeah. When gate is open, water flows in there. Okay, gate is used to moderate the source. Gate is used to moderate the source. Flow rate, yeah, but what is that? Okay, now, no, before explaining, I want you to think over that. All right, gate is controlling, right? Gate, what is gate controlling? Now here, what is, how much ever the valve is open, the drain will drain the water. Oh my God. Oh, no. Flow of water, yeah. Flow of water is the analogy of what? Come on guys, think like engineers. Flow of water is the analogy for what?
Drain terminal.
Drain terminal? No. Flow of water, flow of electrons, correct, Satvik? Very good. Flow of electrons, isn't it? Yes, yeah. I got answers from many of you, Anugna, Samrud, Rushali. And please mind you, don't copy the answers of others. I observed like the one person will enter in the chat box and the others will copy that and paste the same thing. Please don't do that. If you have understood, and if you know only you type. You have to be answerable to your own conscious. Okay. Okay, yeah, that is correct. That the flow of current is nothing but flow of electrons there. Observe that. It is not the flow of the drain current. Drain current will be always opposite to that of the flow of electrons, isn't it? So this analogy, you see there, the drain current, drain is below, right? And source is here. Oh, okay, let me go. Drain and source. So the electrons will be attracted towards drain, isn't it? Okay. And how much of electrons are flowing towards drain is controlled by the gate terminal. And that is the valve here in the analogy. Okay. So the amount of water is controlled by the valve, gate valve here. Okay. In other words, according to our JFET, you can understand the amount of electrons that is getting attracted towards drain, it is controlled by the gate terminal. So the drain current will be opposite to that of this. Okay, you should not get confused there. Okay, the analogy is here. Here, the direction is indicating the flow of electron there. Okay. I hope that is you are able to interpret and understand. Now today I will be uploading the textbooks. Please go through and read. Maybe you'll understand. Okay, and we'll further discuss the drain characteristics controlling VGS in the next class. Anything else? Any other doubt? Any other clarification? Okay, this is the equivalent circuit where you can imagine the JFET replaced as a current source. So this is the indication of a current source. All right. So VDS applied. All right. The varying current, that is the ID. ID will be connected to, say, load like this. So this is an equivalent circuit, keeping VGS is equal to 0 and VDS greater than VP. So when VDS is greater than VP, you know the condition ID will be equal to IDSS. Okay, all these conditions you have to clearly know in order to explain the operation of the JFET. Okay, assuming that you have understood, we will stop today.